So we're starting Unit 8 with a little review on similarity ratios, proportions, and then seeing how this fits together. So remember, we first talked about similarity back when we did transformations with dilations. So what we're going to do in this unit is to explore similarity, but using some geometric theorems and properties rather than doing the transformations. But in order to do that, first we want to talk about ratios. So if you remember, what is a ratio? It is a comparison of numbers. Okay, and we most frequently see ratios as fractions or odds or probability. But remember, a ratio can also compare more than two things, but we typically end up comparing to like length to width, like your aspect ratio of your monitor or your TV. So for example, you can see a comparison of values be written in different ways. So for example, you can have A to B with the colon. We can also have this rewritten as a fraction A over B, which is also that ratio A to B, and of course written in words A to B. So we want to recognize that when we're seeing that in a problem. So for example, if you take a look at example 1, we have a ratio of side lengths of a triangle that is 4 to 7 to 5, and its perimeter is 96 centimeters. So we want to figure out what is the length of the shortest side. Well, hopefully you can see right away that the ratio 4 to 7 to 5 are not actually the side lengths, because 4 plus 7 plus 5 is definitely not 96. So what we do with the ratios, this is basically saying that's that scale factor. You remember that from transformations? This is your multiplier. So if we have some triangle, right, it has 3 different lengths. We don't know what they are, but we know that if we multiply each of these by some number x, we will get that perimeter 96. So we add them all up. And make it equal to that total of 96. So again, we're basically using 4 to 7 to 5 as some multiplier that we're multiplying to some base value x. So again, we can say that perimeter is 15, 28, whatever. It's still the same thing. 4x plus 5x plus 7x equals 96. So we can go ahead and solve that. So 16x equals 96 to get x equals 6. So if we multiply each of our numbers here, 4 times 6, 5 times 6, 7 times 6, we'll get our 3 side lengths. But here we're only looking for the shortest side, so make sure you go back and look at those directions. So our shortest side is 4x, which is 4 times 6, or 24. Okay, so that's how we deal with perimeter. What do you think you'd do if I asked you the same problem but said that the ratio of the angles were 4 to 7 to 5? What do you think that would add up to instead? Well, right, remember our triangle sum theorem says that all the angles should add up to 180, so instead of having 96, we would actually just put 180. Okay, so there's our basics of ratios. So now that we know one ratio, we can also create a proportion. So proportion, which you guys have probably remembered solving before with cross multiplication and all that, it's an equation that sets ratios equal to each other, and specifically it's only ratios that compare two numbers. Okay, so again, an equation that sets ratios equal to each other. When we're solving them, we typically only want to have 2 ratios, but you can put as many ratios equal to each other as you want. Like you can have 1/2 equals 2/4 equals 3/6 equals 4/8, etc. But to solve, we typically just want 2, so that way we can use our cross product property. So we're going to solve using the cross product property. Okay, so that cross product property is what most of us know as cross multiplication. So if we have some proportion A over B, and let's say that is equal to C over D, to cross multiply, we're going to multiply along those diagonals. All right, so I'm going to multiply A times D and then B times C. Right, so then we can create an easier equation to solve, so we can have A times D equals B times C, and then I can divide or whatever I need to do to solve that equation. All right, so if we take a look at example 2, here are a couple proportions for us to solve. So if you take a look at A, what are our cross products going to be? Well, hopefully we all said it's going to be 6x times x equals 5 times 30. It doesn't really matter which product you have on which side, so you can have 5 times 30 equals 6x times x. Doesn't matter because we're all going to get the same value. So here, let's just go ahead and solve this. Remember, 6x times x is 6x squared. 5 times 30 is 150. Remember, before you square root this, make sure you isolate your power. So we're going to divide both sides by 6 to get x squared equals 25. And now we can go ahead and square root both sides. So remember, the square root of 25 has 2 possible answers, so plus or minus 5. Because we have no context to this, we don't necessarily want to eliminate the negative 5, right? We just want to give all possible values to x. So we can solve part B very similarly. Now, what you want to be careful of is when you have an expression, always remember to keep that group together. So let's put z minus 4 in parentheses. And now let's go ahead and do our cross products. So when we do our cross products, make sure you see this becomes z minus 4 times the quantity z minus 4 equals 5 times 20. So you can definitely FOIL this out if you'd like, but what's actually even neater, is that these two are the exact same expression. Oh my gosh, sorry about that. These are the exact same expression, so we can combine that and say this is z minus 4 to the second power, right? And that equals 100. And then since this is one perfect square, right, it's something to the second power, we can go ahead and square root both sides to get z minus 4 equals the square root of 100, which then says the z minus 4 equals plus or minus 10. And now we can split that off and get our two possible answers. So z minus 4 is positive 10, or z minus 4 is negative 10. To get either z is 14, or z is negative 6. So we have two possible answers here as well. So make sure you're careful, right, when you're doing your cross products. Of course, if these didn't match, you definitely want to FOIL that out, and then do your factoring or do your quadratic formula. Okay? So why do we spend so much time talking about ratios and proportions? Because when we talk about similar figures don't have to be congruent, but they will always be proportional. So proportions are going to basically replace congruence in some aspects when we talk about similar polygons. Okay? So let's define again what are similar polygons. So remember, similar polygons are polygons that have the same shape but not necessarily the same size. So if you remember again, dilations, that's when we talked about similarity. Remember, all congruent shapes are similar, but not all similar shapes are congruent, right? Congruent shapes have a scale factor of 1, but we can of course have a scale factor of 2, of 1/8, or whatever. Remember when we talked about similar, the symbol was this thing, this little tilde, so it's basically the congruent sign but minus the equals part. There's two aspects that makes polygons similar. So first, our corresponding angles have to be congruent. So that remains the same when we talked about congruence, right? All our corresponding angles had to be congruent then, and same here. All corresponding angles are congruent as well. But now what's different is our sides don't have to be congruent because we can enlarge or reduce the size of our shape. But now our corresponding sides have to be proportional. Okay, so again, remember, proportional means we can basically make a comparison of one side to another side, and then that ratio is going to be the same for any pair of corresponding sides. So let's look at an example really fast. So let's draw two quick triangles here. So let's call this one ABC. And let's draw another one. Let's call this XYZ. Okay, so by the definition of similar polygons, we know triangle ABC is similar to triangle XYZ if these things are true. So our corresponding angles need to be congruent. So angle A should be congruent to angle X. Angle B should be congruent to angle Y, and angle C should be congruent to angle Z. And in addition to that, our sides have to be proportional. So what we can do is we can compare corresponding sides. So you can see how AB is here on the left, XY is on the left as well. We can put AB over XY, or the reciprocal if you want, right? And then make a comparison with the other pair. So BC corresponds to YZ, so I can put BC over YZ, and then AC over XZ. And that's what I mean by the sides are proportional. Okay? Be careful, make sure you're consistent, right? You will, of course, want to make sure they're the corresponding sides, but then, of course, put the same triangle on top, right? The same sides of the same triangle on the bottom. So be consistent there. Okay? Remember, this is true for all polygons. It doesn't have to be triangles. It can be trapezoids. It can be kites. It can be hexagons, whatever. But all corresponding angles are congruent. All corresponding sides are proportional. All right. And then that ratio that we create for proportional sides becomes what we call the similarity ratio. So that's just the ratio of the sides of similar polygons, which you also know as scale factor. Okay? And your ratio could be the reciprocal of mine. I actually don't care unless I specify. You have to write the ratio from like the larger triangle to the smaller triangle. But if, for example, when we did this proportion here, everything reduced to 1/2, if you wrote 2 over 1, that'd be fine too. Just as long as you have the right numbers. Okay? So if we take a look at example 3, A and B, We want to determine by the definition of similar if these polygons are similar. If so, we're going to write the similarity ratio and the similarity statement. Remember, the similarity statement is just this thing right here, right? Triangle ABC is similar to triangle XYZ. So if you need to determine this, basically tell me a little proof, right? Tell me why or why it doesn't work. So if you look at A, it doesn't matter where you start. I would always start with my angles, and then I'd put my sides together. So let's go ahead and find our missing angle values first. And what do you think we're going to do to find the measure of angle M and the measure of angle T? Well, yeah, we're going to use our triangle sum theorem. However, you can also remember we had an alternative. If you remember this theorem from a while back, it's called the third angle theorem. We can do that as well. So I'm going to start putting together, I'm going to try to see if I can fit a flowchart in here. But remember, you can do whatever format you like. You can write a little paragraph, you can do a hybrid of work and explanation, whatever you feel like. Alright, so there I have my right angle congruence, using those 275s to say angle P is congruent to angle Q. And then finally, angle M is congruent to angle T with my third angles theorem. So that checks off 1, 2, 3 pairs of congruent angles. So now what we need to deal with is we need to put together our ratios. So make sure you think about which sides correspond. So you want to notice that MN and RT are the longer legs next to that right angle, NP, QR go together, and then MP and QT are your hypotenuses. So let's go ahead and put those ratios together. And what we want to show is we want to show that they simplify to the same value. Alright, so I'm okay if you do this, right? You have all your givens and then you just literally create a ratio, because you can compare any two numbers to create a ratio. And then what we want to do is take these given values and then simplify them. Right? So now we should see 2 over 1, 2 over 1, 2 over 1, or if you inverted it, it's fine if you have 1 over 2, 1 over 2, 1 over 2. And then you're not done yet, because remember, to show they're proportional, you have to put it all into one big equation. So let's substitute. Alright, and now we are pretty much done. We have 3 proportional sides, 3 congruent angles, or rather congruent angle pairs. So this statement plus 1, 2, and 3 for our angle pairs now tells us that triangle MNP is similar to triangle TRQ by the definition of similar polygons. Okay, so there's our similarity statement, and then our similarity ratio. Oops. What am I doing? Our similarity ratio is just that number. So just to finish this off, sorry about that. Our similarity ratio is 2 over 1 or 1 over 2. Okay? So why don't you guys go ahead and try B for me. Given we have 2 rectangles, what do you do to prove they are similar, or tell me why there's not enough information? Alright, well hopefully you can read through my messy writing, but I tried another flowchart here. But basically we use our definition of rectangle to show all angles are right angles, which means all of those corresponding pairs are congruent. And then, like I said before, just create your ratios, make sure you show me the simplification, substitute because that proportion is super important, and then we know they're similar, and there's our similarity ratio. Okay? It's got one final example. So what can we do if we know our shapes are similar? Well, remember, if our shapes are similar, we know the angles are all congruent, but we also know that our sides are proportional. So if I am looking for the value of x and I know my shapes are similar, notice how x is part of the side lengths. So what we want to do is we want to make sure we are looking at what sides correspond. So if we look, AC is one of our sides, right? A is the first letter, C is the last letter, so we can go ahead and see what corresponds to that in the second triangle, so x to z. So then we can go ahead and set up our first ratio. And once again, using the sides that were given, we can see BC has a value, 3x plus 1. So BC, the last 2 letters, correspond to YZ. So then I can create my second ratio. And remember, since all sides are proportional, we can set those ratios equal to each other, and now we can create a proportion to solve. Alright, and you'll want to go ahead and do your cross product property, and then solve for x. But remember, there are actually multiple ways to set up the proportion. What matters is your cross products match mine. Remember to be careful, use parentheses, so that way you'll remember to distribute. Alright, so check your work. Remember to simplify your fraction as much as possible. It's fine that it's not an integer. It's fine it's not a pretty number. Just make sure you don't round it unless it specifies you should round. Okay? So that's it for our quick review of similarity, looking at how we can solve now with similarity. And using our definition of similarity, proportions, and ratios. Thanks for listening.